Now, I hope you enjoyed doing those problems. What I would like to do is just have a roundup, a discussion of the summary structures for the questions. So for HCN structure, we have the following. This gave the best Lewis structure because all atoms have a formal charge of 0. For NCS-, that's the thiocyanate ion. The best one was with carbon in the middle with a triple bond to nitrogen and a single bond to sulfur. Sulfur having the -1. And that gave the best structure. Because the NCS- has an overall charge of -1, at least one of the atoms must have a -1 charge. All the other formal charges are 0. So now let's look at exceptions to the octet rule. There are 3 exceptions to the octet rule for drawing Lewis dot diagrams. 1, if you have an odd number of electrons. 2, if you have octet deficient molecules. Or 3, if you have an example of a valence shell expansion, which we've already taken a look at briefly. Let's talk about the odd number of electrons. Nitric oxide is an example of a stable radical. NO is a chemical used in cell signaling in biology and is also an air pollutant. The skeletal structure, well, there's 2 atoms, so nitrogen and oxygen. So the number of valence electrons is 5 plus 6 equals 11. If all has an octet, 8 plus 8 equals 16. The number of bonding electrons, 16 minus 11 equals 5. The number of bonds is 5 divided by 2, which is 2.5. So what do you do if you get half a bond? There must be something wrong. This much must mean that this is an exception. So let's take a look at what the Lewis structure could potentially look like. Well, let's put in 2 bonds. We're going to then complete the octets. So that gives so if we don't use the 2 bonds, that takes care of 4. So 11 minus 4 is 7. 2 lone pairs on oxygen give it a completed octet. And then we have 3 remaining electrons. And if we put those on nitrogen, even though nitrogen has a unpaired electron, it has a formal charge of 0. After you draw your skeletal structure, you need to count the number of valence electrons in the molecule. If you have an odd number of electrons, it is not possible to have all the electron paired. Some examples of molecules that fit into this category are the methyl radical. By definition, if you have a radical, you have an unpaired electrons. You're going to have trouble drawing this structure. You're going to have carbon and 3 hydrogens around it. We're going to count electrons. The number of valence electrons is 4 plus 3 times 1 equals 7. If all have an octet, 8 plus 3 times 2 is 14. Number of bonding electrons, 14 minus 7 equals 7. We have an odd number. We have to realize that this is going to cause us some issues, and we are going to fix that by assuming we can have 1 electron by itself because we have an odd number of electrons. So we're going to assign 2 electrons for each of the carbon-hydrogen bond. That has accounted for 6 of the 7 valence electrons. Hydrogen has its 2 electrons, so now we have 1 electron left. Let's give it to carbon. And what does that mean? Well, you know what? If you have an unpaired electron present in a molecule, you have a radical. Usually radicals are very reactive, but there are some stable radicals. An example of a stable radical is oxygen. So oxygen is a biradical. It has 2 unpaired electrons. But let us follow the rules to see what the Lewis dot diagram predicts as the structure. Number of valence electrons, oxygen is in group 6. 6 plus 6 equals 12. If everybody's got an octet, 8 plus 8 equals 16. Number of bonding electrons, 16 minus 12 equals 4. 4 divided by 2 equals 2 for our number of bonds. So that means that we should get the following Lewis dot diagram. Double bonds, and then that means that that's accounted for 4 of the electrons. So 12 minus 4 is 8. That means there's lone pairs. Putting them on 2 lone pairs on each of the oxygen gives us our octet for oxygen. But if we actually look at the properties of O2, it shows that it is a biradical. There are 2 unpaired electrons. So in fact, this shows that Lewis dot diagrams doesn't give the complete story. There is another category of exceptions to the octet rule, and these are the octet deficient molecules. Some molecules are stable even though there are 2 fewer than 8 electrons. So let's take a look at an example. BF3. Here is a structure following the rules for BF3. We could have fluorine with a double bond, and that gives boron an octet. And then we have a -1 on boron, and fluorine is +1. Now, who says that that particular fluorine gets the double bond? We could move the double bond around to the other fluorines, and so that creates a resonance structure. But think of it. We have a +1 formal charge on fluorine, which is the most electronegative in all the periodic table. So let's think about relaxing the octet rule and let boron only have 6 electrons. That gives us the following structure here. And when we calculate the formal charge, what we have is we have a molecule with an overall charge of 0, and each one of the individual atoms have a formal charge of 0. That gives it the best Lewis structure. So group 13 elements, for instance, boron, aluminum, gallium, and indium, can be octet deficient. This is an example where having a 0 formal charge is better than having an octet. So all the elements in that row are happy and stable without a octet, and they're good with 6. Another example of our exceptions to the octet rule are valence shell expansions. So let's start by going through an example, following the systematic approach, and see how we can learn and figure out when things are going to go wrong. So 1, draw the Lewis dot diagram for the molecule SF6. Well, first of all, let's think about how we're going to set up the structure. Well, there's 6 fluorines and 1 sulfur. Let's put sulfur in the middle. Number of valence electrons, sulfur has 6, each fluorine has 7. That gives us a total of 48. If each atom has an octet, that means that we have 56. That means 56 minus 48 is 8. That will give us our bonding electrons. 8 divided by 2 is 4. That says that there are 4 bonding electrons. Okay, but there's 6 fluorine atoms. How can there only be 4 bonds? Well, it's not going to work. So what you should immediately realize is that if you don't have enough bonds to make your molecule, that it must be an exception. And you can't use the systematic approach to draw your Lewis dot diagram. So then let's just connect up the sulfur and the fluorines, each with single bonds. That has used up a total of 12. That means we have 48 minus 12, which is 36 extra valence electrons. 36 divided by 2 is 18 lone pairs. And 18 is a nice even number because 18 divided by those 6 fluorines means that each fluorine gets 3 lone pairs. And when we do that, each one of those fluorines then have a complete octet, but there are 12 electrons around sulfur. This could create issues. Oh, but look, when we calculate the formal charge on sulfur is 0. So it's okay. We have the best Lewis structure because all the elements have a 0 formal charge. So what's with sulfur? Sulfur can break the octet rule with 12 electrons, and the answer is yes, it can. If the central atom is large and have empty orbitals, it can hold additional pairs. This only occurs in nonmetals from period 3 or higher because they have the empty d orbitals. And if they've got the empty d orbitals, their magic number is not 8. It can actually go above 8 if they make use of those d